Welcome to this online workshop on the use of topic models in corpus linguistics. So before we start, so we are going to do hands-on session later. So can you go to this URL? Can you try to access this URL here? So basically it's tinyurl.com, 𝗵𝗵𝗲, standing for Topic Models Workshop, and today's date, 2020-08-05, so August 5th. This includes all the necessary files, like corpus files and R script, R markdown, etc. And we'll use the data that you can download from here later. You can download it to wherever you can identify the path of. So basically, you need to specify the path in the R later. As long as you can identify the path, you can download it wherever you want. And once you are done with downloading, can you please extract or uncompress the file so that they are accessible from within R. And for the next few slides, I'll put the URL at the bottom right hand corner so that you can check. So today I would first like to start with conceptual introduction to topic models, because I assume most of you are not very familiar with topic models yet. And after that, we'll move on to hands-on with R. Altogether, the workshop for this session is supposed to last 60 to 90 minutes, so 1 hour, between 1 hour and 1.5 hours. And I do not assume any knowledge of topic models. I'll explain what they are in this session. But I do assume some familiarity with R, that if I ask you to run certain command, you can run it. You can specify the path of the file. Okay, so what is a topic model? Well, one challenge in corpus linguistics is to develop bottom-up methods to explore corpora without imposing pre-existing distinctions. And in order to address this issue, I'll introduce the use of what's called topic models, which is a machine learning technique that automatically identifies topics in a given corpus. And I'll explain what topics are, because they're somewhat different. Okay, probabilistic topic model basically automatically identifies topics in a given corpus. And the word topic model is a cover term. It includes a range of different types of models. But the best known model and the best frequently used model of topic models is what is called the latent data allocation, LDA, which is the most popular type of topic models these days. And what it does is it identifies keywords in each topic, and also identifies distribution of topics in each document. So each topic consists of actually the mixture of all the words in the corpus, but with different probabilities. So some words are more likely to occur in certain topics than others. Also, a document or text is a mixture of topics. So each document includes all the topics, but with different probabilities. So a particular text has high probability of topic, 3, but low probability of topic 5, etc. A topic, in turn, is technically a probability distribution over words. So basically, as I said, the topic is a mixture of terms and is often characterized by a group of co-occurring words in documents. So if a certain word is frequent in this document, then this another word is also likely to be frequent in that document. So that sort of pattern is what characterizes a topic. Methodologically speaking, LDA is a technique to analyze document term matrices, which are basically a list like this. So it's basically a list of the frequency of each word in each document. So here you can see each row corresponds to each document, whereas each column represents each word. In this particular example, the word intelligent occurs twice in document 1 and once in document 2, and doesn't occur in document 3, etc., etc. So this is the primary, well, not the primary, this is the only, primary input data for topic models. What it means in turn is that it is a bug words approach. It does not really look at the text as a sequence of words. It just looks at the list of words and the frequency. Okay. If you're a corpus linguist, you might be familiar with multidimensional analysis developed by 𝗏𝗏𝗏𝗏 and used by a lot of people. Topic models are functionally similar to multidimensional analysis, although they are algorithmically very different. So multidimensional analysis identifies co-occurrence patterns of various linguistic features that are often abstract. So something like nouns or that clauses or relative clauses, those things. And then analysts give those co-occurrence patterns functional or communicative interpretations, like informational versus involved. Topic models, on the other hand, identify usually a larger number of, so multidimensional analysis typically identifies up to something like 10 dimensions or 10 factors, whereas topic models often identify something like 100, 200 topics. And so topic models identify a larger number of co-occurrence patterns of individual words rather than linguistic structures. And then topic models give them a thematic, typically, and give them thematic or rhetorical interpretations. And the difference in the interpretation comes from the fact that topic models look at individual words, so they are like content words, for example. Usually it's not content words; they exclude function words. They look at content words which are informative as to the thematic content of the corpus, whereas multidimensional analysis looks at more like grammatical structures which are more informative as to the functional and communicative like intents. So that's sort of the difference, but those two techniques are quite similar, functionally speaking at least. So how does a topic model work? Yeah, I see. I just found there's a chat and there are lots of chats here. Okay, right. Yeah. If you have, yeah, I forgot to mention this. But if you have questions, can you post it on? Can you type in the chat, and then I'll have a look at them later and try to answer the questions. So how does a topic model work? This is the assumed generative process of each word. So we assume there's a die that is specific to each document, and the die is irregular. And we roll a die, we roll the die, and the face of the die determines the topic we get. And we then roll another die that is specific to the topic. And the face of the die we get determines the word that we observe. So this is how you assign a topic to each word in each document. So that's what topic models do. Topic models assign a topic to each word in each document. And this is the process that is assumed to underlie each word. This is a probably more intuitive schematic illustration of how topic models work. Let's say there are 100 documents here. Because there are 100 documents, we have 100 irregular dice. So we roll an irregular die as many times as there are words in the particular document. So if there are, I don't know, 1,000 words in document 1, we roll the die specific to document 1 1,000 times. And the number of faces of the die equals to the number of topics in the corpus. And once we roll a die, so okay, yeah, we use the same die for the same document, but we use different dice for different documents. And the face we get determines the topic of the word. These dice are irregular because certain topics are more likely to occur in a document than others. The document typically has something with themes. It's not like an equally balanced set of topics. Now, once we roll a document-specific die, we get a topic. And for topics, we have a different set of irregular dice. The number of dice we have equals to the number of topics. And then the number of faces equals to the number of word types in the corpus. And the face we get determines the individual words. Again, we use the same die for the same topic and different dice for different topics. And the face we get determines the word we observe. These dice are irregular because certain words are more likely to occur under a topic. The word ecological, for example, is more likely to occur when people are discussing climate change than when we discuss, I don't know, Shakespeare. And this procedure of rolling dice is repeated as many times as there are words in the corpus. Now, the corpus is basically a collection of text. So the most column is what we observe. This list of words is what we have. But what we are interested in is here. This like underlying process and underlying dice. And what topic models do is they reveal the shape of the dice and basically the shapes of the dice involved. Topic models reverse this word generation process and estimate the probability of obtaining each face in each die. So we are interested in the shape of each irregular die in this schematic illustration. For example, we can ask how likely is it that we get topic 5 in document 1? Is that a predominant topic or is it an unimportant topic at all? We can also ask how likely is it that we get the word water in topic 8? And is topic 8 relevant to water in any way, or is it not? And these are among the quantities that the topic model estimates from the data. And when we combine kind of information with the metadata of the corpus, we can do something interesting, as we see later. So how does a topic model specifically reverse the process or estimate the probabilities? The topic model assigns a topic to each word type in each document. There are multiple parameter estimation methods proposed in the literature, but one of the most often used methods for parameter estimation in topic models is Gibbs sampling, which is a form of MCMC, Markov chain Monte Carlo, which in turn is a parameter estimation technique that is commonly used in Bayesian statistical modeling. Topic models, at least LDA, is a type of Bayesian statistical model, technically speaking. So how does it work? Well, intuitively speaking, once there are two principles that compete against each other. One is that once many tokens of a word have been assigned to topic J across documents, the probability of assigning any particular token of that word to topic J increases. What it means is that, so for example, if the word water is given topic 1, any other occurrences of the word water are also likely to be given topic 1. But there's this another principle, which says once a topic J has been used multiple times in one document, it will increase the probability that any word from that document will be assigned to topic J. So in other words, we want to have as few topics as possible in a document. Now, these two principles compete against each other. Let me illustrate it with a toy, with a small corpus, including only 3 documents with 3 words each. Let us say we want to identify 2 topics in this toy corpus. And let's say we randomly assign topic red to the first word in document 1, so word X in document 1. Following the second principle, we want to assign topic red to all the other words in the same document. Then we can notice that word Y, the final word in document 1, was assigned topic red. So we want to assign topic red to all the other occurrences of word Y in the corpus, following the first principle. Then we can see that word Y, one word in document 2 was assigned topic red. So we want to assign topic red to all the other words in the corpus, in the document, following the second principle. And now word Z was assigned topic red, so we want to assign topic red to all the other occurrences of word Z following the first principle. Then we end up having only 1 topic, although we might need to identify 2 topics. So this is a complete failure. Topic models will give something, balance the 2. And here we identified 2 topics, topic red and topic red, topic red and topic blue. Although in document 2, we now have 2 topics, a mixture of 2 topics. So both topic red and topic blue are in document 2. So this is the sort of thing that topic models do. And in practice, all the documents are the mixture of all the topics, just with different probabilities. At a bit like higher level or practical level, or functional level, I should say, there are primarily, so there are primarily 3 pieces of information that we can extract from topic models and are relevant to interpretation as far as corpus linguistics is concerned. First of all, we can identify the probability of each topic in each text. We can say something like topic 1 occupies 2.2% of text 4. And if you are familiar with multidimensional analysis, this is similar to dimension scores. So we can basically situate each text in each topic. Second of all, we can extract the probability distribution of each topic over word types. So we can say something like the word author occupies 3.2% of topic 15. And this is similar to factor loadings in multi-dimensional analysis. So it basically shows which feature is associated with which dimension in the case of multi-dimensional analysis. And in the case of topic models, it shows which word is associated with which topic more strongly than which word. And finally, we can extract the assignment. We can see the assignment of the topic to each word type in each text. So we can say something like the word beach was assigned to topic 10 in text 7, something like this. And we'll see how we can identify these, how we can build a topic model in R and how to extract these 3 types of information from it later. A few further methodological issues here. So topic models can be used in any language. Text can be tokenized. I've seen it run in many languages, including things like Japanese, for example. Since MCMC gives something involves randomness, the results of MCMC-based topic models can differ each time we build a topic model. So the results are not strictly reproducible if you run it as is. So it is therefore important to set a seed in the case of R, so that the results will be reproducible. So there's no global solution to there can be multiple local solutions. And yeah, please see our paper comparison between those additional techniques, keyword tagging and collocational network, etc. Okay, let us then move on to hands-on sessions. But actually, before that, does anyone have questions? I've seen. Okay, oh yeah, there's the Q&A tab here. Yes. Right, yeah, right, yeah. How do you deal with documents that have multiple topics? Yes, a document can consist of multiple topics, and it is represented as a mixture of topics. So yeah, we can identify different proportions of topics we text file. So another question is that, is this an unsupervised method? Yes, this is an unsupervised machine learning technique, just like clustering. Wouldn't you okay, wouldn't you have to segment discourse first somehow? No, and as long as we can identify words, so as long as we can make the frequency list, basically the word list, it is fine. And let's say spoken discourse. So we need to, we need to be able to tokenize a text. We need to be able to identify individual words there. But as long as yeah, we can make a list of words. we can identify a mixture of topics. Okay, then we must label the topic previously. Okay, right, yeah, that is a good question. We'll go over the procedure of building topic models later, but just like multidimensional analysis or just like exploratory factor analysis, it is up to us to interpret each topic. And we do the interpretation iteratively, just multidimensional analysis. We look at the list of keywords, and we look at like what kind of words are, what kind of topics are more prominent in what kind of text, and if all of it is considered, we give appropriate labels. Okay, so I am thinking how to get to the level of documents, so Nico. Okay, so I sort of assume there's, right, yeah, yeah, that's a good question. So yeah, I kind of assume that there is a text already, and we apply topic models to that text. And I would say it would be better if you can somehow segment this course into texts with reasonably coherent topics. It will be easier. It will come to be easier to analyze in that way. It does not automatically segment. No, topic models do not automatically segment. It just what they do is they identify the proportions of various topics in a given text. The unit of analysis is basically a text. So each observation comes to be a text. Sven, it's an interesting question. So is setting a random seed really desirable? Isn't the randomness a desired feature in machine learning algorithms? I mean, even if you set a seed, the result is kind of random. It's just that it comes to be reproducible. And when you, for example, write a research paper based on topic models, you probably want to set a seed so that other people can completely reproduce the results. So for the sake of reproducibility in research papers, I would say we should probably set a seed if we use topic models for research purposes. Anthony Lee, what's the difference between the topic models and the keywords? We'll come to that later, but topic models basically group up keywords, and it makes it easier to interpret the keywords in the sense of keywords analysis. Is it concerned with any abstract topics, Muhammad? So a topic is basically a co-occurrence pattern of individual words. And if that pattern of co-occurrence can be interpreted to mean something abstract, then it can be interpreted in an abstract manner. So whether it identifies abstract topics partially depends on the text and partially depends on the interpretation of the researcher. Can we do the hands-on part? Yeah, that's what I thought. Yeah, let's go on to the hands-on part. Right. Okay, so yeah, I'll explain a bit about the corpus that we're going to use. So, okay, so these, we'll use the books available as part of the project Gutenberg. And I randomly downloaded 200 books each from science fiction and children's book stories. So there are two genres. A book can contain multiple topics, and it will be interesting to divide books into multiple parts because it allows us to investigate topic transition within books as well. Without this, we can identify a mixture of topics within a book. So we can say this book consists of 5% of topic 1 and 7% of topic 2, etc., etc. But we cannot say something like topic 1 is more prominent at the beginning of the book, and topic 7 is more prominent at the end of the book, etc. So more specific, to sort of like isolate this, to look at the transitional topics within a book, it'd be interesting to divide a book into multiple pieces. So what I did was I divided each book into text blocks with approximately 300 words each. And so the metadata of this corpus includes genre, so science fiction or children's stories. And each document was assigned with the information on where in the book the text block appeared, so something like 70% from the beginning of the book. And the file name of the corpus looks like this. And the first part corresponds to the book ID in Project Gutenberg. And this part, so the red part, the digits that follow indicate the position within the book. So 0.49 means 49% from the beginning of the book. In total, there are approximately 36,000 text blocks from 400 books. And together, the corpus include roughly 12 million words. Okay, let's then move on to let's look at the files. So in okay, so have you downloaded the zip file that I asked you to? I'm not sure if you could, but if you did, these are the files that you must see besides this zip file. This zip file is what I distributed. And so it includes the slides that I used in just now. And this HTML file is basically an R Markdown file, including all the R code and the output of the code that we are going over just now in a minute. And this topic models ws.r is an R script that we're going to use. And this rdate file includes a topic model that I'm going to explain this to you as we go on. And this metadata underscore text CSV include metadata. It basically lists the ID, book ID, and the book, whether it's children's book stories or SF, standing for science fiction. There should also be this folder corpus, and in this folder there are two subfolders. One is children, the other one says SF, so including these two sub corporal genres. And each file, as I said, should look something like this. And the first part identifies a book, which book it is. So book ID of Project Gutenberg, and then the position of this text block within the book. And each text file should be relatively short. Then let us. Okay, then can you open RStudio, or R if you prefer, and open this R file, R script, topic models ws.r. Let me switch to that screen. Okay, so the, sorry, yeah. So do you see this file like this? I hope you do. So did you, so Tony, did you run these lines? So, okay, can you please all run these first 5 lines? These are the lines that allow you to install all the packages that you have not installed if you haven't.
Okay, let me try that, Akira. Thank you.
So the lines from 6 to 12 list all the libraries that you need, and these are the lines that you load, that you use to load those packages. But the first 5 lines basically check whether you have installed those packages already, and if you haven't installed the ones that that you do not have. And so if I just run these, you know, they're obviously I have installed everything already, so there's nothing that needs to be done. And while you're installing, let me explain what, or roughly, what each library or each package is. So if you have trouble installing, you can install each of these in turn. I mean, you can just, you know, write something like install packages and npm or topic models or something like that. You can do this like one by one. I just thought it might be easier to, you know, do it automatically. So I just wrote this. Okay. Yeah, so the first package we use is TM. General text mining purposes, and the topic models package we use heavily depends on this TM package of various functions offered in the TM package. So we load this. So it is used in constructing document style matrices, etc. Second of all, and this is so there's a package called topic models, which is the package that performs topic modeling analysis, and so it includes LDA function that constructs topic models, as well as many other functions that are specific to topic models. So we load that as well. 𝗬𝗏𝗟 package, we just use one function from there, and the function is called _stem, which is used for stemming. And stemming is a kind of like soft lemmatization in a way, and I'll explain what it is as we go on. Scales are not particularly necessary, but when we draw a figure, I just wanted to use this function called %format, which transforms small number, decimal point representation of percentage into percentage. So 0.49 is turned into 49. That's the whole purpose that I use this package. Tidy text includes an exhaustive long stop words list, and I just wanted to use the stop words list in the tidy text package. So let's read this, and I'll explain what stop words list is when we get there. Okay, F size package is just for the calculation of an effect size that we're gonna look at later.
and 𝗪𝗪𝗏. 𝗪𝗪𝗏 is a collection of packages that are useful for data visualization and data handling. Okay, have you largely succeeded in launching RStudio and installing and loading necessary packages? If you have a significant trouble, you can you can open up this HTML file that I distributed, and it shows all the output that is necessary that we will look at. Okay. So okay. First of all, let us read the text files. So in the data that I distributed, there's a folder called corpus that we have just looked at, and we will read all the text files included in there. And for that purpose, we use this corpus function and also their source directory source function in the TM package. And here, instead of saying corpus, you should specify the path of this corpus folder. In my case, the corpus folder sits directly under the current working directory, so I don't have to specify the path specifically. I can just write corpus here. But if you download it and uncompressed your file somewhere else, then please specify the path to your folder here. And then can you okay, then this line, so corpus row, etc., basically allows you to read the corpus. It takes a while, but it does read the corpus. And okay, yeah, I forgot to mention this. So recursive equals to true means it reads subfolders as well. It does not just read the corpus directly under corpus folder, but it reads subfolders included in the corpus folder. And pattern equals to .txt means we just capture .txt file. Okay, so we are done with reading. So let's look at this corpus row object. If you just type corpus row and just run this, this is what you see. And what it says is, it doesn't give you much information. It just says there are 3,000, about 36,000 documents, as we expected. So we can see that all the documents have been read accurately. In order to look at the content of the corpus, we need to use this function. There are multiple ways to do this. One of the ways is to use this content function. And if you do something like this, we can specify the first two files of this corpus row object. And to see the content of it, we use content function. And if you run this, you can see something like this. And then, indeed, you can see the content of two files. But you can also see that there are some meta characters. So, for example, \n is marker of line breaks. It's not just it's not. So if you see a text file, it's not here. It's just it's just a line break. And because of these meta characters, it can be a little difficult to inspect. In such a case, we can include this whole line content corpus row 1 to 2 in the cat function. And if you run this line here, then all the line breaks are really turned into line breaks. So you can see, you can now see that there are different lines. It's not just a chunk of text. So for humans, this is probably easier to read. Okay, let's clean up this corpus a little bit. First of all, let's just get rid of all the line breaks, and also for some reason there are 2 hyphens that are used just like word boundaries. So let's break up here. If you say could not find function corpus, the function corpus is included in the TM package. So what that means is TM package has not been installed. So you can, before running that code, that line, you can write something like install packages that here. You can run this, and then after that, if you load a library, if you load the TM package again with this, and then you should be able to load or read the text files. And what is it? Right. So let's clean the text file. So basically, we just create. We replace line breaks and these 2 hyphens into a space. And after that, we get rid of everything that's not alphanumeric. So basically, numbers and also digits and alphabets or space. Everything besides those things will be gotten rid of. We basically replace it with nothing, which means we get rid of it. And this is a bit. So this is the way you can do it within the TM package. So this is the 𝗬𝗏 global substitute, and you replace with this. And let's run it. It probably takes a while, but it's not going to be so long. And we now assign the resulting object to a variable called corpus.cleaned. Okay, it's done. We now look at the first 2 files of the cleaned corpus. Here, we can see that all the line breaks and the punctuations, so everything that is not alphanumeric has been deleted, which makes it a bit easier to process. Okay. Sorry, you don't see this chat here. So if it says empty directory, that so 𝗫, what that means is your corpus folder is not there. It's not directly under the working directory. It has to be, so you have to specify the path, file path to the folder where you uncompressed the zip file that I distributed. So that's probably. Okay, so we will, right, now that we have cleaned the corpus, and to what extent you should clean the corpus depends on really the purpose and the type of the text included in there. If punctuations are are important for some reason, you probably want to retain them. Here, I just, okay, so yeah, so the input data to topic models is a document term matrix. So we have to create a document term matrix. And here are the parameters for the document term matrix. To lower equals to true means all the words will be converted into lowercase. So we do not distinguish uppercase and lowercase letters. Again, if for some reason, if you think it's good to distinguish, then you may not want to specify this. So there's no longer punctuation here, so I don't think this line is necessary, but we keep it here. But this line basically says we ignore punctuations. So remove punctuations equal to true. So we get rid of all the punctuations. We, however, retain numbers. So remove numbers equals to false. So often numbers are not so informative as to the topics. So people often get rid of numbers. But let's say we just, and people often use a stop words list and in running topic models. What it means is, so stop words are basically a set of common frequent words. And particularly function words like articles and prepositions are usually not very informative as to the topic of the text. So people often want to get rid of them. And here, we do the same too. And for that purpose, we use a stop words list in the tidy text package. And this is how you specify it. Stop underscore words $word. So if you just run this part here, you can see the list of words that are excluded. So these are the words that have been excluded, like or, as, or. And there are lots of words that have been excluded here. Okay, Tony, right. That's included in, so pipes, they're included in tidy text, tidy verse package. So just like before, you want to install packages. And you probably want to do the same for the other packages as well, like topic models and tidy text, normal C. And right. And as stop words, you can specify other lists as well. So the TM package also has stop words for English. And in the TM package, you can say TM that colon stop words and English in the parentheses using quotation marks. And TM package, the stop words in TM package total only has 174 words. You can also specify stop words in the typical R way in a vector format, as a character vector on series. So here's how you can specify the stop words. And although stop words are often excluded in the topic models analysis, whether you should really do so is a bit difficult issue. Many words here could be in corpus linguistics perspective. From the topic models, if you use it, right. So yeah, whether you want to exclude it, I don't think there have been many studies. I actually don't know any study that investigated exclude stop words on the results of topic models. And so you probably want to consider or think about whether or not to exclude stoppers and what kind of stoppers to exclude. I just wanted to show, that because this is what people often do, really just do it here, but but one issue. Okay, right. So yeah, and stemming, yes. So we also apply Porter's stemming algorithms. So it's a bit like lemmatization. So the word required becomes require, and it chops off the third person S and other things. And you can do so when we think about topics, which are basically like thematic information. Things like lemmas or stemmed words can be better units to use rather than surface forms. We don't necessarily want to distinguish requires and require when thinking about topics. Tony, that's included in a package. So again, if you do install packages tidy text, then that should be. Right, and it is often useful to specify target word length in order to exclude something like statistical terms like P's and T's, etc. in the analysis of research papers. And to do that, you can do something like runs from 2 through infinity. So it basically excludes all the one-letter words, but still retain everything else. Here, let's not worry. We can include everything. Okay, can you please run this set of code? So lines 31 to 47. So it's basically a list including all these arguments. And we now create a document time matrix with a function called the document time matrix. And that is included in the TM package as well. The first argument of the document time matrix is corpus. So in our case, it's corpus.clean. And to the control argument, we pass the list we have just created, DTM.control. And so let's just run it. And we assign this list to the object called DTM. Okay. Yeah. Okay, let's examine it. If you just look at DTM, here's what you see. Document time matrix with, it says there are approximately 36,000 documents and 57,000 terms or words, and non-sparse entries. So 36,000 times 57,000. So this times this should be this number. Actually, it's not. So something like that. Okay, I see. No, sorry. All right. So this is number of cells that is 0, and this is the number of cells that is non-zero. So if you think about the document time matrix, you might be able to see that most of the cells will be 0. Most of them say, the part says let's say like 0. Most of the words do not occur in most of the documents. And sparsity is 100%, which means the vast majority of the cell counts at 0. Maximal term length is the number of letters of the longest word, and it says 146, which is a bit weird. And I looked into this, and it's just a URL of a website, and it's not part of the book. It's part of the metadata of the book, which we didn't really clean up. So, but in the real research, you probably want to get rid of them. weighting, you don't have to worry as long as topic models are concerned. So, okay, in order to look at the inside of the document term matrix, so this is basically the sort of like metadata of the document term matrix. In order to look at the inside of the document term matrix, you need the function called inspect. And here we inspect or look at the first 5 rows and the first 5 columns of the document term matrix. If you run this, you can see something like this. So you can see that in the first 5 documents, none of these 5 words occurs anywhere. Right? So they are numbers, but they are words. So the word 0001 occurred at least once in the entire corpus. So that's why it is listed here. But it's not. It did not occur in any of these 5 text files. 5 files. You can, however, specify the specific words here. So time and don't. We got rid of punctuations, so apostrophes are gone as well. And again, if you use inspect, you can see something like this. So there are several documents listed here, and just the words don't and time. So the word don't occurs 10 times in this first text file, 7 times in this text file, 6 times in this text file, etc. The word time occurs, doesn't occur here, 3 times here, etc. So that's how you can look at the document term matrix. If you apply dimension, standing dimension function to the DTM object, you can see that there are 36,000 documents and 58,000 words, which is too many. There are too many words here. Because most of the words, as I said, most of the words do not occur frequently, and those words are not particularly informative to sort of like distinguish documents. So what people often do is they only retain the words that occur in at least 0.1% of the in at least 1% of all the texts. So basically, a word needs to occur in at least something like 360 texts in your case. And this is how you can do it. There's a function called the remove sparse terms in the TM package, and you throw in the document term matrix and the percentage, 0.99. And we look at this dimension again, then we can see there are now only 1,842 words. So these are the words that occur at least in 1% of all the documents. Okay, and if you look at the first 5 rows and 5 columns, you should be able to see that the terms, the words are retained are more frequent. So the words like 0001 were gotten rid of because they are not that frequent. Now what retains is the words like abroad, abrupt, absolute, academic, probably, etc. So they're frequent words. And these are the words that we're going to target in the topic model. Okay, now we are ready to build a topic model. So this document term matrix is the input data to the topic model. So we can now build a topic model. In a topic model, just like exploratory factor analysis or multidimensional analysis, we need to, we analysts, researchers, need to specify the number of topics. Okay, and what people sometimes do is they build topic models with different numbers of topics, like a topic model with 10 topics, a topic model with 20 topics, 30 topics, 40 topics, etc., and then decide the number of topics by comparing the results, just like factor analysis. But here, okay, and also there are some attempts to automatically identify the optimal number of topics. And if you look at something called structural topic models, there's a way, and I think they supply a function that allows you to choose the optimal number of topics. But here, let's just go with 10 topics. We go with, we decide to build a topic model with 10 topics. So n that topics equals to 10. How can we determine the optimal number of topics? So it's a bit like multidimensional analysis. There's no like absolutely accepted way to do it, but we usually, so what people do is people build topic models with different numbers of topics and compare the results and see which one best captures what we are interested in. So at some point, so if you know, for topics, for example, we can probably not appropriately label each of them. We cannot really distinguish a topic from another topic. Whereas if you only look at 3 topics, that is 2 cores. And the optimal number of topics is a matter of like interpretability. Topic models are essentially an exploratory approach. So we specify the number of topics depending on whether the results bring us interesting insights into the corpus. And okay, right, yeah, we go with 10. Are there statistical methods for that? There are some attempts. I don't think there's any like agreed way to do it. There have been some attempts in LDA as well. And if you look at structural topic model, or our package of STM, structural topic model, which is an extension of LDA topic model, I think they have a way to, they proposed a way to do it fairly easily with R, and they identify the optimal number of topics as well. Okay, so we need to specify other arguments passed to the LDA function that allows us to construct a topic model. So the first 3 are just the details of MCMC. So if you know what these are, yeah, these are the values. And if you don't know much about MCMC, don't worry. That it doesn't really, I mean, it usually doesn't affect the results so much as far as topic models are concerned, probably. Yeah, as long as you go with these numbers. If you change these numbers radically, then it will be different. Okay, and then here's where you set a seed. And if you put if you put seed equals to 200, then the results will be reproducible as long as you use the same version of the software, R, etc. And you set the same seed. Okay, let's read this. So this is a list including these arguments, all right? Then please do not run this code because it takes a relatively long time, something like 10 minutes. I mean, it's not like a very long time, but still, we cannot do this within this workshop. So this line of code takes about 10 minutes to run, and this is a code you use to build a topic model. So LDA is the function that allows you to build a topic model, and the arguments are, first of all, the document time metrics. So in our case, it's DTM. And second of all, it's the number of topics. In our case, it's 10 were included in and that topics. It says method equals to 𝗬𝗑𝑠, which means we are going to use 𝗬𝑠 sampling. And to the control argument, we pass that list we have just created here. And if you run this, okay, so I ran it beforehand. I ran this and I saved it within this 𝗷𝗂𝗇𝗏 file. So SFC, SF plus children, underscore divided, so divided into text box, 10 topics, dot 𝗷𝗂𝗇𝗏. And I distributed it in the zip file. So again, if you uncompressed it, unzipped it from somewhere else, you need to specify the path here. But because it's directly under my working directory, I can just read it. So if you just read this, you should have the object, an object called TM. And if you just type in TM, I think, it just says, LDA gives topic model with 10 topics. So that's what we. Okay, how do we explore a topic model? There are multiple functions that allow us to explore our topic models. And they are almost always the functions included in the topic models package. And okay, first of all, there's a function called terms, which extracts keywords in each topic. And the first argument of the terms is the topic model. So in our case, TM. And this part, the second argument specifies the number of keywords we want. If you run this, you can see that there are, you can see top 10 keywords in each topic. And you can see, in one example, the most prominent keyword is time, followed by night, uncle, house, told, brown. These have been, you can see these have been stemmed. Uncle without E. And one thing that you can notice is that keywords can overlap with, between topics. So like word time here, for example, occurred here, but also here, in topic 2. But what's interesting is they often have somewhat different meanings. So here it's like time, night, uncle, house, brown. If you look at this, it's a bit like nighttime, bedtime, something like that. Whereas here, if you look at the keywords, it's like people, time, world, life, day, person, nature, live, or some mind. And I thought it was something like time travel, or some kind of different, slightly different nuance of time is here. So, but the point is, keywords can overlap with between different topics. Okay, what is it? So there's also a function called the topics, which allows you to look at the key topics in each text. And so this is the number of key topics. And we just look at the first 10. On this, we can see something like this. So for this particular text, the most prominent topic is topic 10, followed by topic 1, and followed by topic 9. And here it's topic 10, 1, and 4. And this is 10, 1, 4 again. But no wonder, because they are taken from the same book, just with different text blocks. We can also look at the probability of each topic in each text. And to do that, we use a function called posterior. So we look at posterior distribution. And dollar mark topics means posterior distribution of topics. And we use head function just to look at past texts. Here, so what it says is topic 1 occupies 13% of this text, and topic 2 occupies 6.7% of this text. Topic 3 occupies 5.4% of this text. So if you add this up horizontally, it will be 100%. Okay. And so this is the topic in each text, right? You can also look at the probability of each topic in each word type. So if you look at posterior TM data terms, and you need T to transpose and head. You can see something like this, but because of these scientific notations, it's a bit difficult to see. So you scientific force, you get something like this. Here, you can see, for example, topic 2 is represented by words like accept and absolute better than words like academic, abrupt, abhorred, accident. So here, if you add these values up vertically, it will be 1. So which words are represented in which topic? So that's the sort of thing that is shown here. The words ranked in each topic. It's a not just frequency though. I mean frequency in the sense of like how often that word was assigned to that particular topic. So if you remember the word generation process, so actually it might be easier to see this here. Okay, yeah, I think it's easier to see here. So you can see topic assignment of each word type in each text in this manner. We need to go through this bit like involved process just because of the way sparse document time matrix is represented in the TM package or in R. But details aside, if you run this 116, and the token accident, or I think accident was given topic 4, animate animal was given topic 1, appear was given topic 8, etc., etc. So you can see the topic assignment each word in each text. That's what topic models do. And the keyword of each topic is basically the words that are assigned frequently to each topic. So the word, if the word accident was assigned a lot to topic 4, then the word accident is considered as a keyword in topic 4. So it's a frequency of assignment of each topic to, each word type to each topic. Okay, let us do a bit of interpretation of topics. I don't go into the interpretation much, but you know, we can combine the kind of information we have just seen with the metadata. And let's read the metadata. And again, you need to specify your path to this CSV file. And this metadata just includes the book ID and the genre. Okay. And let's add the text ID with the position information and the position information to this metadata. And please don't worry about the details of this R code. If you run this, what it does is it just adds, you know, so it separates out the ID. So no, actually no. It has text ID and the position information to the metadata. So the metadata just included ID and genre. We now have text ID and position number as well. Okay, so that's metadata. But we still haven't added the results of topic models yet. And that's what we do here. We now create a data frame including by text. So by text topic probability, so topic probability for each text in the so-called long format. But let's not worry so much about the details of this R code. And if you just run this and look at this by text object, you can see there's now the information about topic probability. So there's topic, there's a column that says topic, and there's a column that says prob, standing for probability. So what it basically means is in this text, the probability of topic 1 is 12.8%. And okay, yeah, and to help the interpretation, we can sort this data according to the topic probability. Okay, so first of all, this is the keywords. We are looking at the first 20 keywords of each topic. And if you look at topic 3, it says something like hand, fire, head, hold, sudden, arm, feet, shout, kill, quick, drop, shot, dead, gun, fight, etc. So it looks a bit like, you know, fight, or maybe possibly a war kind of topic. And we'll see whether it is really the case. And if you run these 3 lines, what it basically does is it sorts. So actually, it only looks at topic 3, and it sorts the data according to the probability of topic 3. So basically, this is the text with the highest probability of topic 3. And actually, about half of the text, 49% of the text is occupied by topic 3. And this is here, 48% of the text is occupied by topic 3, etc. And we can look at the actual text in this manner just by specifying the full name of the file. And we don't have time to read this carefully, but if you look at the first few lines, so okay, yeah, we are going back to the text now here. Crowd data. Instead of a crowd data, we can actually raise a crowd data. If you cannot find the crowd data, can you try to install a newer version of the 𝗵𝗨𝗖𝗏? It might be a relatively new feature of the 𝗵𝗨𝗏 function. Or instead of saying crowd data, you can instead write that. That should work as well. Yeah. Instead of saying this, you can say something like this. Yeah, so we do go back to that text data here. I mean, we can use words, and we also look at the text to interpret. So here's the text of concern. If you just look at the first few lines, you can see something, you know, but he was not defeated yet, facing his more powerful enemy, roaring unceasingly, and with a shrill piping whistle of the battle, the younger bull fairly swelled with exertion and rage until he seemed almost the size of his big foe. So you can see it's a and based on this kind of characteristic texts combined with keywords, you can try to interpret and give an appropriate label to each topic. let us finally draw some figures to see topical differences between the two genres. Here with this GG plot, we draw a box plot demonstrating the difference between the topics. And so we can see that there are some topics like topic 2 and 7, and probably 8, where SF is more prominent, whereas others like topic 4, 5, 9, where children's book stories is more prominent. And this is just, impression from the figure. So we can calculate the effect size between the two. So they are not normally distributed, so we should not use t-test or something. We should probably use a Multidimensional U-test and then a relevant effect size here. And the detailed side, here's how you can calculate the effect size and look at the results. You can see the largest two, the second largest difference is observed in topic 4, etc., etc. And finally, we haven't really looked at the position. We haven't exploited the position information yet. So if you look at, if we draw this GG plot, you can see that it takes a while. But so you can see that children's books 1, 4, 9, whereas science fiction is more prominent in topics 2, 7, 8. And also you can see patterns like topic 10 is more prominent at the beginning and at the end of children's book stories. Or in both science fiction and children's stories, topic 3 tends to go up as the story develops. So you can see this kind of pattern based on topic models. Mention one last thing here. If you look at the first, look at some of the keywords. So both topic 4 and topic 9, I think it was prominent in children's book stories. But you can see topic 4 is a bit like boyish children's stories, like Tom, and car, horse, etc. Other keywords, whereas topic 9 are characterized by more a bit like girlish children's book stories, like girl, miss, father, lad, mother. So you can identify multiple types of differences between subcore, in this case, children's book stories and science fiction. If we run keywords analysis, these two topics are likely to have been combined, and it just gives a list of words. Whereas if you run topic models, they in a way automatically group up meaningful, make so meaningful groups of words. So that's one key distinction between the keywords analysis and topic models. Okay, sorry, I ran out of time, but I'm not really ran out. I ran over the time for 2 minutes. But this is about it as to how to run a topic model with R. Do you have any questions? In the QA side, okay. Maya, how do you have how you compiled, prepared corpus? Okay, yeah, I use R to interested in the R code that I made the corpus with. Can you email me, and I'm happy to send you the R code that I used. Can you paste the reference to the articles? If you look at the final page of the slides that I included in the zip file, so in the zip file that I distributed includes the slides that I used today. And in the final page of the slide, there's a list of references. Yes, that one. Thank you, Tony. Okay, if you don't have any more questions, thank you very much for attending my workshop. I hope you enjoyed it. And if you have any more questions, can you please email me?